Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will use what we know about transformations to graph cubics and other functions. Let's start by looking at the graph of y equals x cubed, a cubic. So let's start by looking what happens as x approaches infinity. So that's just a shorthand mathematical way of saying what happens as x gets larger. Well, as x gets larger, y also gets larger. But then what happens to y as x gets more and more negative? So as x becomes a larger negative number, y also becomes a larger negative number. So this is different to the parabola. When you cube a negative number, you get a negative number. When you cube a very large negative number, you get a very large negative number. Unlike parabolas, whereas in a parabola, if x approaches minus infinity, y approaches positive infinity. It also has what's known as an inflection point at 0, 0, the origin. You'll become a lot more familiar with inflection points as the years go on. But now let's put this information together to graph y equals x cubed. So we have our axis here and the inflection point is here. Now what happens is as x gets larger, y also gets larger. It becomes more and more positive. So the graph is going to go up like this. But as x approaches negative infinity, it becomes more negative. So as we're going across here, y approaches negative infinity. So it goes down. So the graph looks like this. So all cubic graphs have this inflection point. It's sort of like a point where the graph is divided into two pieces. We've got this piece up here and this piece up here. Both of them kind of look a little bit like half parabolas. So I want to make the point that y equals x cubed is an odd function. So that means you would get the same graph if you reflected it about the x-axis or you reflected it about the y-axis. Remember, our definition of an odd function is this. It's an odd function because if I take this formula and replace x with a negative x, I get this. So I have f of minus x is equal to minus f of x. So we can use what we know about this graph of y equals x cubed to graph other cubics using what we know about transformations. So we're now going to graph y equals 2 minus x cubed. It might be easier for you to think of this as y equals minus x cubed plus 2. These two formula are exactly the same. So the graph of this will be the same as the graph of y equals x cubed, except it's just had two transformations applied to it. Firstly, this plus 2. Remember, adding a constant moves it up or down. So this will be the same as this graph here, except moved up 2 units. And this negative in front of the x cubed reflects this about the x-axis. Of course, because it's an odd function, we'll get the same result if we reflected it about the y-axis. So let's draw up our axes and graph this. So for this graph of y equals x cubed, its x and y-intercept was 0. When x equals 0, y equals 0, right? But because this has been moved up 2 units, the y-intercept will be moved from 0 up to 2. And the only other thing that has changed is that it has been reflected about the x-axis. So let's look at this. What would it look like if it was reflected about the x-axis? Well, it would look like this. This here in red would be the graph of y equals minus x cubed. So this graph over here will look like this red one, except it will go through y-intercept of 2 instead of 0. And there we have it. How easy is that? So because of this negative in front of the x cubed, because it's a reflection about the x-axis, for this graph, the same as what happened for the red graph over here, is as x approaches infinity, as x is getting larger and larger, y is actually going towards negative infinity, becoming more negative. And the opposite, as x is going along here and becoming more negative, y is becoming more positive, larger, more positive. So as x approaches negative infinity, y approaches infinity. All right, let's quickly do one more graph of a cubic using transformations. So let's now graph y equals 2 outside of x minus 1 cubed plus 4. So this is a cubic because we've got an x to the power of 3. And we've just taken the graph of y equals x cubed here and applied some transformations. So first we have to identify these transformations. Hopefully you remember this minus 1 shifts the graph 1 unit to the right. So this 4 here, this plus 4, shifts the graph up 4. Now this 2 in the front, we haven't talked about a lot. It's actually just a dilation. It stretches the graph. What it would do to y equals x cubed is just make it get bigger faster. So I graphed over here y equals 2x cubed, what that would look like. It looks like y equals x cubed. It's the exact same shape. It just is a bit narrower. It gets larger faster. It gets more negative faster. That one's a hard one because it depends on the scale, what the dilation will actually look like. Whereas these two, moving right and up, you can see that regardless of what the scale is. So I'm not going to worry too much about the 2 in this one here. All right, let's go ahead and graph this. All right, so we have our axis set up. Now we know that the inflection point of y equals x cubed is 0, 0. So when we move to this right 1 unit and up 4 units, think of this as moving the inflection point by that amount. So we've taken our inflection point from here, we've moved it right 1 unit and up 4 units to here, 1, 4. So there in green is where the inflection point would be. Now, because this is a positive number in front, unlike this one which was negative, the same thing here is going to happen as what happened there. So what I mean by that, as x approaches infinity, as x gets larger and larger, y will get larger and larger here. If you substitute a very large positive number for x, y will be a very large positive number. Similarly, if you substitute for x a very large negative number, then y will give you a very large negative number, okay? In other words, this is going to go like this way. It's not going to go this way because there has been no reflection here. So we might also calculate the y-intercept because that is easy. The y-intercept is just the value along here that the graph hits. It's the y value when x equals 0. So if x equals 0 in this formula here, we have this. So we just substitute 0 into this original equation to get this, and you can put that on your calculator. You get y equals 2. So the y-intercept is 2. So because we have these points and we know that the graph is going to go like that, we can graph it very easily. And there we have it. All right, sorry for the long video. Thanks so much for watching. This has been the luckiest maths teacher in the world. Have a great day.